Here's a concept map that I've crafted as a way to represent and summarize the key concepts and the relationships to one another from this week's chapter. Before I begin, I would just like to say that this chapter will be very similar in nature to the next two chapters that we do. All three, without a doubt, deal with hypothesis testing, but there's one big difference. In this chapter, we're dealing with a single sample mean. In the next chapter, we'll be working with two sample means. And in the third chapter, we'll be dealing with at least three sample means, if not more. If you take a quick look at this week's concept map, you'll notice that I've used color to denote different clusters of coherent ideas. But even more, you may discern the use of a gray dashed line in a significant part of the concept map itself. This is important. Although I have used colors to denote particular clusters throughout the entire concept map, the cluster joined by gray dashed lines represents the big idea for this particular chapter, and it is of great practical consequence for our work here. But let's begin at the top part of our concept map. Hypothesis testing with a single sample mean allows us to compare a sample mean to a population mean, and it allows us to determine if a sample is reasonably representative of a particular population. For us to determine what this reasonably means requires us knowing where the sample lies in the sampling distribution of sample means. It also requires knowing whether or not a sample could reasonably come from a given population with a particular mean, in other words, particular mu, and a particular standard deviation, or sigma. When carrying out a hypothesis test with a single sample mean, a few things are required of us. Namely, they involve 1. Formulating a research question, 2. Knowing how to structure that research question, and 3. Knowing how to test that research question. Conducting a hypothesis test with a single sample mean, or two sample means, or three sample means is an essential element of inferential statistics, and it involves quite simply a statement of one's expectations. But we can put it a little differently. It is a way of testing for extreme values or extreme scores, and so we are looking for a significant difference between the sample mean and the population mean. And where there is a significant difference between a sample mean and a population mean, it is said that there is a low probability of the sample having occurred by chance. Such an extreme value of a score is said to fall in the critical region or area of rejection of the sampling distribution. This area has to be defined in advance by the researcher. Should a value happen to fall within this particular area, it leads the researcher to reject the null hypothesis. The area is defined by a critical value, and this value marks the beginning of the critical region. All hypothesis testing begins with the statement of a null hypothesis, and there's particular notation to keep in mind here. A null hypothesis is represented by a capital H and a small subscript O. This is read H naught. The null hypothesis is a testable hypothesis, and it may be read or understood as taking a number of different forms. That is, we can read a null hypothesis as being a statement of no difference between a sample and a population. It could also be read as a statement of no relationship, or a statement of chance. Either way, however the null hypothesis is stated, they all mean the same and are all represented in the same fashion. So, this brings us to the practical matter of describing the steps of a hypothesis test, and in this case, doing a hypothesis test on a single sample mean. In a bare bones kind of way, this is the process for constructing a hypothesis test with a single sample mean. We begin with 1. formulating a null hypothesis. 2. Setting a level of significance. 3. Identifying a critical value. 4. Calculating a test statistic. 5. Evaluating the test statistic in light of the critical region or region of rejection. And last but not least, step 6, making a decision about the null hypothesis. Back to the beginning, we see that step 1 involves formulating a null hypothesis. In other words, our null hypothesis, H0, is going to be a statement of the form, there's no difference between the sample mean and the population mean. For instance, assuming that we're looking at a single sample mean, which we are in this chapter. We then have to set the level of significance. This must be done in advance of the rest of the test itself. We will set the level of significance at 95% or 99%. After that, we have to identify a critical value. And the critical value, as noted earlier, will define the critical region or the area of rejection. We then need to do a calculation. We need to develop and calculate a test statistic. This test statistic will depend upon whether or not we know the standard deviation for the population, or we don't know the standard deviation for the population. In the case that sigma is known, we would then use the z-score table to calculate our test statistic. If we don't happen to know sigma, then we need to refer to the family of t-distributions in order to calculate the test statistic. We then need to do a comparison, or to evaluate the test statistic in light of the critical region or the region of rejection. Either our test statistic falls in the critical region, or it doesn't fall in the region of rejection. Based upon that, we are then in a position to make a decision about the null hypothesis. Last but not least, we could be wrong about our decision. We could be wrong if we found a significant difference and ended up rejecting the null hypothesis. In other words, if our null hypothesis was that there is no difference between the sample and the population, and then we found a significant difference between the sample mean and the population mean, then it would be said that we'd be committing a type 1 error. This is also called a alpha error. And this happens with a particular probability equal to the level of significance. We could also be wrong if we didn't find a significant difference and failed to reject the null hypothesis. In other words, if we did not find a significant difference between the sample mean and the population mean when we should have. In this case, we are committing a type 2 error, and this is sometimes called a beta error. And with that, it might be good to take a dark room moment and return to your readings or this concept map to read it one more time a little later. But for now, this is the end of my reading of the concept map for hypothesis testing with a single sample mean.